Grounding both a transformer and a panel to the same grounding electrode does not violate National Electrical Code Section 250.6. This section specifically addresses the connection of the grounded conductor to the grounding electrode system. In the scenario presented, the grounded conductor is not connected to the grounding electrode system at the transformer. Therefore, Section 250.6 does not apply. Consider a three-phase pad-mounted utility transformer with a primary voltage rating of 13,200 volts and a secondary voltage rating of 480W/277 volts. The transformer and the panel it serves are located on the same pad, approximately 4 feet apart. The design specifies that the transformer is grounded to a 4/0 copper conductor embedded in the pad. Furthermore, the three-phase conductors and the grounded conductor are installed to the panel, which is also grounded to the same 4/0 copper conductor. The question arises whether this installation violates Section 250.6 of the NEC, given that grounding both the transformer and the panel to the same grounding electrode might create a parallel path involving the grounded conductor and the grounding electrode system. To understand this, it's crucial to examine what 250.6 covers. Section 250.6 pertains to objectionable current. Objectionable current refers to current flowing on grounding conductors or grounding paths. Such current can create issues such as voltage drops, noise-insensitive electronic equipment, and potentially even pose a safety hazard. The NEC aims to minimize objectionable current through proper grounding and bonding techniques. However, not all current flow on grounding conductors is objectionable. For instance, during a ground fault, current will naturally flow through the grounding path to trip a circuit breaker or open a fuse, thereby clearing the fault. The key is to differentiate between normal, expected fault current and unwanted, continuous current flow. The code specifically addresses scenarios where the grounded conductor is intentionally connected to the grounding electrode system at multiple points. This can indeed create a parallel path, allowing current to flow on the grounding conductors under normal operating conditions. This is typically undesirable. However, in the case described, the grounded conductor is connected to the grounding electrode system only at the panel, not at the transformer. The transformer is grounded separately via the 4/0 copper conductor to the grounding electrode system. This distinction is crucial. Since the grounded conductor is not connected to the grounding electrode system at the transformer, there is no parallel path created at that location for normal current flow. The connection at the panel serves to establish the required grounding for the electrical system, ensuring a low impedance path for fault current to return to the source. The NEC recognizes the importance of grounding both the transformer and the panel. The transformer grounding ensures that the transformer itself is at ground potential, preventing dangerous voltage buildup. The panel grounding ensures that the electrical system within the building or structure is properly grounded, providing a safe path for fault current. Grounding both to the same grounding electrode system is permissible and often the most practical approach, especially when the transformer and panel are in close proximity. This arrangement helps to minimize impedance in the grounding path, which is beneficial for fault current clearing. Now, let's consider some general principles of grounding and bonding to provide a more comprehensive understanding. Firstly, grounding refers to connecting an electrical system or equipment to the earth. This connection is typically made through a grounding electrode system, which can consist of ground rods, ground plates, underground metallic water pipes, or other approved electrodes. The purpose of grounding is to stabilize voltage to earth during normal operation and to provide a low impedance path for fault current to return to the source. Secondly, bonding refers to connecting together all metal parts that are likely to become energized, such as metal conduits, metal enclosures, and equipment grounding conductors. Bonding ensures that these metal parts are at the same electrical potential, minimizing the risk of electric shock. Effective grounding and bonding are essential for electrical safety. They help to prevent electric shock, reduce the risk of fire, and protect sensitive electronic equipment from damage. When designing and installing an electrical system, it is crucial to adhere to the requirements of the NEC and other applicable standards. This includes properly sizing grounding and bonding conductors, selecting appropriate grounding electrodes, and ensuring that all connections are made correctly. In summary, the described installation, where both the transformer and the panel are grounded to the same grounding electrode system, does not violate NEC section 250.6 because the grounded conductor is not connected to the grounding electrode system at the transformer. This arrangement provides effective grounding for both the transformer and the panel, ensuring electrical safety and proper system operation. Remember to always consult the latest edition of the NEC and seek guidance from a qualified electrical professional when designing or installing an electrical system. This ensures compliance with all applicable codes and standards, as well as the safety of personnel and property. Furthermore, consider the impact of any local amendments or regulations that may apply to the installation. Local jurisdictions often have specific requirements that supplement or modify the NEC. Always verify these requirements before commencing any electrical work. Also consider the following aspects of grounding and bonding. 1. Equipment grounding conductors. Equipment grounding conductors provide a path for fault current to return to the source. These conductors are typically copper or aluminum and are sized according to the overcurrent protection device protecting the circuit. 2. Bonding jumpers. Bonding jumpers are used to connect metal parts together to ensure electrical continuity. These jumpers are typically installed around knockouts, conduit fittings, and other points where electrical continuity might be interrupted. 3. Grounding electrode conductors. Grounding electrode conductors connect the electrical system to the grounding electrode system. These conductors are typically copper and are sized according to the size of the service entrance conductors. 4. Supplementary grounding. In some cases, supplementary grounding electrodes may be required to improve the effectiveness of the grounding system. This is often the case in areas with high soil resistivity. 5. Surge protection. Surge protection devices, or SPDs, are used to protect sensitive electronic equipment from voltage surges. SPD are typically connected to the grounding system to provide a low impedance path for surge current to dissipate. 6. Maintenance and testing. Regular maintenance and testing of the grounding system is essential to ensure its continued effectiveness. This includes visual inspections, continuity tests, and ground resistance measurements. By understanding these principles and adhering to the requirements of the NEC, you can ensure that your electrical system is properly grounded and bonded, providing a safe and reliable source of power. Note that this information is intended for educational purposes only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or electrician before making any decisions about your electrical system. Furthermore, always refer to the latest edition of the NEC and any applicable local codes or regulations to ensure compliance. Keep in mind that electrical codes and standards are constantly evolving to reflect new technologies and best practices. Staying up to date on these changes is essential for ensuring the safety and reliability of electrical systems. In addition to the NEC, other relevant standards may apply, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. These standards provide guidance on various aspects of electrical design, installation, and maintenance. Consider also the specific requirements of the equipment being installed. Manufacturers often provide detailed instructions on grounding and bonding, which should be followed carefully. These instructions may supplement or modify the general requirements of the NEC. Finally, remember that electrical work can be dangerous. Always take appropriate precautions to protect yourself from electric shock and other hazards. This includes wearing appropriate personal protective equipment such as safety glasses and insulated gloves, and de-energizing circuits before working on them. If you are not qualified to perform electrical work, hire a licensed electrician. Electrical safety is paramount.